Welcome back to another code review. Now I'm going to review the deep learning algorithm, the IQL algorithm that uses the deep Q networks for multiple agents. So we're going to try to train our 5 robots to do some soccer behavior. And before I start, I'll show how the code is organized. So to train our deep reinforcement learning algorithm, we should use our train.py script. That's our main file. And this file communicates with other files. Similarly to the rule-based example, we have a helper that auxiliates us with distance and other functions. Also, we have our reinforcement learning utils.py where we design our state, action, and reward that we already know that's really important for our algorithm. And then we have our algorithm.py, and in this example is going to be the dqn, the dqn.py. And this is linked to two other files, the episode memory where I have my replay buffer and I save the experience that my agents get during training. I save here to use for training, and I have my networks.py where my neural network architecture is implemented. So we're going to go through all these codes right now. The first one is going to be my train.py, and as usual we will start with our libraries import. Here we have our math and our numpy that we use for numerical computation, and the special imports are going to be our helper that we're used to and our deep reinforcement learning algorithm that is the dqn. So from dqn, that's from dqn.py, we import our dqn class that's going to train our algorithm and also save our experience, everything we are going to use in this class. And from reinforcement learning utils, we have our get action, so it's our action design, our get reward, that's our reward design, our state, where is our state design, and also have two more things to help us. That is a logger that will help us to print and plot the graphs for us to see our reward, and a touch counter. A touch counter is another thing that helps us, that is going to count when a robot touches the ball. So he counts the subsequent time steps, so I give rewards to the robots just when they kick the ball. So for example, if the ball moves to the good direction but the robot didn't kick, he did not influence into that ball movement, so he cannot receive any reward for that. He just can receive reward when he acts in a way that he deserves the reward. Our constants that at this time already use it too, so we have the reasons that the game can be reset, like a score from my team or a corner kick situation. We have the possible game states, that is the default game state, or when a kickoff, a goal kick, a corner kick, or a penalty kick happens. And I have my constants that help me in my program, that's my team, opponent team, X, Y, Z, that makes also my code more readable. I also add some robot index here as constants in this example, in the sample code. And after I train my model or during training, I create some checkpoints where my trained model is being saved. So this is in my models folder. So I train the policy for the goal. I save the policy for the goalkeeper, defenders, and attackers. At each time step, I receive my frame that consists of time, the current score, the reset reason, the current game state, the image, the coordinates, and if it's the first or second half. We know that the player class that inherits from the participant, we have three main functions that the gamer should change. The init, that is called before the game starts, where it have all the important information from the game. You have the update, that you receive the frame at every time step, and you also have a finish that we don't use here because we don't need to do anything after the game is finished. So we're going to start with the init. In the init, we load the files from our parameters.json. that this file is just to help the gamer to change variables quickly, to train their algorithm. For example, the neural network is defined in this place, and I'm going to show later. We get the information about the field, dimension, the maximum linear velocity for the robots, the goal dimensions, the number of robots, the end of frame. The end of frame is important because after the end of frame is true, we know that we received all the information from the AI soccer simulator successfully. Here we also create the variables views, where we're going to put our continuous variables that we're going to send back to the simulator. And we have the current posture of our robots, the previous posture of our robots, the current posture of our opponents, the current ball, and the previous ball. Also say the previous frame. Here we have a frame skip variable that we use to help improve our exploration. So we repeat the action for this value, the same action, so our exploration is a little bit better and we get better results. I'm going to explain this again later. So using our state design, we have that the dimension of our state is 10. So we use this value to be the dimension of the input of our neural network. We have our action sites. Here we use like 13 discrete actions. So this is the output of our network. If you have doubt regarding that, you can watch my presentation regarding the introduction to deep reinforcement learning. So here I also, for reinforcement learning, I get my action, previous action, state, previous state, reward, previous reward. And we know that the deep neural network algorithm is implemented in the DQN class. So as I'm using independent Q-learning, I have one network for each robot, so I need to initiate the class one time for each robot. So here I create a trainer variable that contains 5 DQN classes, one for each robot that I can use for training. And then I initiate the touch counter class to help me to calculate the reward. And I initiate variables that can help me count the rewards, and also the logger to help me plot the reward. I have the get coordinate function, where at each received frame I update the current ball, the current posture, the posture of my opponent, my previous posture, the previous posture of my opponent, and the previous ball. After I receive the update, I receive all the information successfully after end of frame is true, and I can start. So similar to the rule-based ones, I just update the coordinates I receive. If it's the first frame, I do not have a previous frame, so I initiate the previous frame with the first frame I receive. And I also update the touch counter. So I update the touch counter here. After update the touch counter, I can get my reward for this time step. So I get that and put in the self.reward variable. So for each robot, I get the reward associated to each robot. So I get 5 rewards, 1 for each robot here. And I give all the information I need to calculate the reward is here, including the touch counter and including the reset reason. And then I get the state. So I use the get state function and give everything that I need to calculate my state here. And when I receive the state, I receive also one state for each robot, because we know that our state design for each robot is different. So I get the state I calculated and reshape and put in the way that I can use as input of my network in this self.state variable. And every frame skip time steps, I get my action. For example, if frame skips 2, I get my action now based on my exploitation in the trainer. So trainer select action, I get my action, and I also update the reward. If not, I just repeat the same actions I used in the previous time step. After now I define my state, reward, and action, I store my experience in my replay buffer. So I say to my trainer, if my robot is active, so like if my robot is not active, I don't need to update the experience because it's useless experience. So if my robot is active, please store my experience in the replay buffer. So we store my state, action, reward, and next state in my experience buffer, because I'm going to use that to train my algorithm. And I also as I also have the action, I can send the information back to my AI soccer simulator. So I get the updated wheels here, and I send using the set speed function. And to each robot, I do one training iteration of my neural network using the update function. And I also call the save checkpoint, that if my frame attains the condition, I'm going to save the checkpoint. Here in this part, I'm just saving and plotting the reward graph, that I'm going to plot the graph to check throughout the training if my agent is learning or not. The end of this train.py is that I update the previous state, previous action, previous reward. Now the reinforcement learning utils. In this reinforcement learning utils, I start by loading my libraries, and what we see here that some other libraries that we use is matplotlib, numpy, and in this we use torch as a deep learning library and also the helper. The constants one more time. And this time we need to get some constants related to torch, because you can run torch using your GPU or without using your GPU. So I get this information if you're running using your GPU or not. That this will be important during training. I have my touch counter that I count the steps after my robot kicks the ball. So usually I count for 20 steps after the kick. So what this means is that after the kick, the next 20 time steps are still useful, like to get reward. After that, my robot did not influence the action. So I update the counter using this function, and I have the counts where I update the counter, and I can get the value using the touched move current, touched go current, using this function. Here I predict the ball velocity and the robot velocity, and I'm using the ball velocity to calculate my state. The state design is implemented here in the get state function. So here in the get state function, I'm going to calculate the state for the goalkeeper here, for the defender, and for the attacker. What it changes is that for the goalkeeper, he does not have a teammate, so he doesn't know the position of other robots. But the robots that have a teammate, they know the position of their teammate, like here, that the one knows the position of the two. In addition, they know the position of the ball in relation to their current position, the ball in related to our own field, their own orientation, the error orientation relative to the position of the ball, and the ball velocity. That's the main things used for the state. For the reward, I have the reward that are based on the distance between here in the basic. I have the reward that is to the robot to learn to chase a ball. That is based on the distance between the robot and the ball, the orientation error, and the ball robot velocity. So the robot receives more reward if he's near the ball and with the right orientation in the direction of the ball, and also moving towards the ball. I use the exponential function here because it improves the learning and it's much better than linear functions. So there are a lot of literature on that. And I also have the differential reward. The differential is if I kick the ball and I kick the ball in the good direction, it means like to the opponent field or to the opponent goal, I receive a reward. Just in these situations. If I kick in a bad direction, I don't receive any reward. This is the differential reward. And to finish, I have the score concede reward. If my team score, I receive the score reward. If my team concede, I am punished. For the goalkeeper, the reward is relative between his distance to the defense position to protect against kick, the differential, and the concede. Our defenders just want the basic and the differential reward. And our attackers, basic, differential, and they also want to score. And the action, the discrete actions, are here in the get action function. So I have 13 discrete actions that implement actions like go forward, go backward, rotate, and stop, and kick. So for more information regarding these actions, you can watch the introduction video. And finally, the logger, just to plot the reward graph for us. In this sample code, the helper is just simple because I just have three functions here to calculate the distance, the defense kick angle, and to print message in the console of Weebot. So just 3 functions. An important file is the dqn.py. That's where the dqn algorithm is implemented. So in this, I need to import the neural network architecture from the agent class that is in the networks.py. I should import the torch library and the functions that I need to use to train my algorithm. And I import the copy to copy our target networks, the NumPy, that's the numerical computation library, the helper, the experience replay buffer, that's the memory, and other libraries. So when I initiate the dqn in the train.py, what I initiate is that I receive the number of agents that I have, I receive the checkpoints where my model is being saved, and to stability I have a target network. So I updated my target network every 100 time steps, and I explained before that we have exploration and exploitation. At the beginning of the training we explore. So we are taking random actions. When we are taking random actions, we have the epsilon greedy algorithm that the epsilon is equal to 1. But at the end of the training, or when I'm playing, I'm exploiting because my policy already know what to do. So my epsilon can be like a small value, like 0 when I'm playing, or 0.1, so 10% of random actions at the end of the training, because I still want to explore different strategies while I'm training. So these variables are really important. The epsilon steps, the epsilon, the final epsilon, and the decrease epsilon. So the epsilon here, it starts with 1, so 100% random actions. And every epsilon steps, every this kind of iterations, I decrease my epsilon by 0.025 until I get my final epsilon of 0.1. After 0.1, I don't decrease anymore. So if you want, for example, more exploration, you should increase the value for self epsilon steps here. That is defined in the parameters of JSON. So here you have the epsilon steps, that is 30,000, so can increase that to get more exploration, for example. The observation steps is the number of steps that I see before I start training. So here right now it's 1,000. I'm going to decrease this later for us to check the beginning of training here in this video. And the save number, so every 5,000 I save my checkpoint, and I have my batch size that is also imported from the parameters. The number of inputs depends on our state design. The number of actions depends on our action design. Our memory, our replay buffer, our neural network that's in the self.net, our target network that's in target net. Load, it means that if we're going to load a trained checkpoint, or if you're going to train from scratch. And here is related to torch. So if I'm going to train my network, if I'm using the GPU, my gamma is like, my gamma influences the future rewards. How important are future rewards? My learning rate and my optimizer. To select action, we just use eGreedy. So we receive the state to select our action, and we have a probability to select a random action, and this probability is calculated using epsilon. So for example, if epsilon is 1, I'm going to always pick a random action. If epsilon is 0, always I'm going to pick the action that my network picked in this line here, where I pick like the network, I give the state, and he predicts my Q value for the actions, and the action that I choose is the action where I have my maximum Q value. So I mean, like, I'm going to choose the action that's going to maximize my future rewards. Here I store the experience, so when I receive the experience to store, I store in my replay memory, so self memory push, and I store my state, next state, action, and reward. Update policy is where I implement my DQN algorithm. So I get my batch of data, that is a lot of experience that I collected before. So I calculated my target here, and I calculate the error between my estimation of my network and my target, and I try to minimize this estimation so that after training my estimation corresponds to the real target value. So after that, I implement my backpropagation using the backward function, and I optimize my weight using self.optimizer.step. So every update steps update my target model for stability, and also I update my epsilon every self epsilon steps. Here I save my checkpoints. So I save every save number. I save my latest model, and every 200,000 iterations I save a checkpoint. Here I have my print loss, and finally the updates that I call in my train.py. So I get my iterations and I update the policy, and I print the loss if I have to. My neural network architecture is here in the networks.py. So we can see that I have the agent class, and I define the number of layers here, the number of hidden dimensions here, and I have my layers. And I'm just using linear layers, and you see here that for my range of number of layers, I calculate my middle linear layers and use ReLU nonlinearity. And with that, I have my Q value as the output. And I also have the save model just to save my weights and my trained model. So this is a really simple architecture, the number of layers and hidden dimensions that are defined here in the parameters. So if you want to change the architecture, it's really easy to just come here to parameters.json, and I change the number of layers, and I change the hidden dimensions, I change the neural network architecture. And I have my episode memory, that is just a buffer where I store experience that I had, so I can push, so I'm saving new information to my memory, or I can sample, and I use sample to create my batch size. So I create my batch size with random experience from this buffer. So when I want to train, I get, for example, 128 experience randomly, and I try to train for that experience. This is my parameters.json. Here we are training the IQL, so we have the gamma, that's how important future reward 0.99, my batch size, my buffer size, 200,000 iteration, my learn rate, my epsilon steps, that is regarding the exploration, my clipping to make my training more stable, my neural network architecture, the algorithm that I'm using. This is what you probably should change in your algorithm. And finally, I have my play script. After I train, I can use my play script to check my model. So my play script is really similar to my training script. So I have my checkpoints here, and I initiate my variables. really similar variables, but now to the play I just need the variables to calculate the state and action, because I do not need to calculate the reward because I'm not training anymore. And now for the play I need this self-load and self-play, because I want to load my trained model and I want that he exploit only, so I want to play. So load and play are set to true because I want to exploit and I want to use my trained model. In the update, I just calculate my state, and from my state I calculate my action, and from my action I assign my wheels and I send my wheels back to the AI simulator, finishing my play script. So with this I went over all the training script, and we can try to initiate some training to check this working. For that, because to make the video shorter, I'm going to change that we just observe 100 time steps here, and I'm going to save to see the beginning of training in our screen. So I'm going to get reboots here. So I have reboots, and you see here that I'm using my multi-IQL DQN examples and train.py. Another thing that we should change actually is because right now you're using the game time, the default values for game time and deadlock, and we're not repeating. But you can imagine that we are going to train for a long time, and actually we need to set the repeat to true so we can repeat for a lot of games. And at the beginning of training we do not know like how to chase the ball, so the deadlock will be always active. So we can deactivate the deadlock and put the game shorter so you have more data that is similar to each other. So let's run here. Let's see if it works. And we're training against a random walk algorithm. So you see that he begins here and he starts to take random actions. Both are taking random actions, but our algorithm takes the random action for the 13 actions, discrete actions that we define. So after 100 iterations, you see that it started training. So we show the agent that's training, like if it's the defender or the attacker, like the value of epsilon 1 means that 100% of taking random actions, and the loss of the network is like how different the estimation is for the real value. But we are at the beginning of training, so both the estimation and the real value are really wrong, so we need more time actually to train this algorithm. Here I'm going to show you, because I already trained this before for around 1 day, and we got this kind of graph. So you can see that at the beginning, if I just take random actions, around 1.5, but as the training goes, my reward is increasing until I get a plateau right over like 3, the value of 3. So see that actually I reach a maximum because I end my exploration. So right now I'm really exploring less, and I kind of learn the behavior. So let's see if the robot learns how to chase the ball by using the play script here. So we're going to start again, and we're going to see if it learns something. Yeah, you can see that he starts to chase, and he already like knows better how to chase. He's going to chase the ball, and he's going to try to score, especially because he's playing against random walk. So he can really easily score, but he committed a foul. But again, he's playing against a random walk. He's going to have another chance to chase the ball. Let's see. and F2 gets near and he scores. Yeah, so you see that he really learned to chase the ball, the behavior, and also to kick sometimes. If I play for more time, you could see that more. But one problem that you can see already is that as I trained only against random walk, he's not specialized against better teams. One way to solve that, for example, is that you can specialize playing against yourself, for example. So I will try to do that right now. So I'm going to, here in the training, now I want to start the training with my trained model. So I know that this trained model has a good model. So I'm going here and I'm going to say that I want to start, so I want to load my trained model, and I'm going to give my trained model here. But I also don't want to start exploring from random completely, because now I'm competent, so I want to exploit more and just explore a little bit to play against myself. So I'm going to keep epsilon like 0.1. I'm going to keep epsilon 0.1 so I can train. And I'm going to use my trained model here. I saved my trained model in a models trained file, and I'm using that to play against me. So in the play file, I'm going to change the checkpoint to model trained. So I'm always going to use this fixed checkpoint. And save. Now I open my reboots again, and now this is going to be my opponent. This is going to be my opponent, and I'm going to start to specialize my trained model to play against myself, my old self, because I want to get better than he is. So I start the trained again, and you see that he's going to start to play, but now the opponent is not random walk, is also competent, and they're trying like to play a real match. Now I need to start overcoming my old self and get better at every time step. But my old self is trying to score against me. So you see that the goalkeeper was really bad, and this is also important to specialize, because when playing against random, the goalkeeper does not get opportunity to improve because the opponent is really bad. But now playing against a good opponent, the goalkeeper can be better and learn, we hope that he can learn useful behavior. And we start to train again. And now the epsilon is just 0.1. With that, we finish this code review. I hope you enjoyed, and if you have more questions, get in touch with us, and see you in the next video.